The other primary continuous probability distribution that we'll discuss is the exponential probability distribution. Exponential random variables are typically used to describe the interval between occurrences, for example, time or distance. Recall from our discussion of discrete random variables, a particular discrete probability distribution was the Poisson distribution. With the Poisson distribution, we know a rate of occurrence per interval, and we want to calculate some probability of the number of occurrences in that interval. For example, say failures on a piece of equipment occur at a rate of 3.2 failures per month. A Poisson distribution would give us the probability of 6 failures in the next month. With the exponential distribution, we have that same rate, some number of occurrences per interval, and we want to calculate the probability that the interval until the next occurrence is some value. In our failure example, the rate of occurrence of failures is 3.2 per month. An exponential distribution would help tell us the probability that the number of months until the next failure is 1.3 months. A few more comparisons between the Poisson and exponential distributions. In the Poisson world, we might ask, what is the probability that between 3 and 5 customers arrive in the next 15 minutes? In the exponential world, we might instead ask, what is the probability that it takes 15 minutes for the next customer to arrive? With Poisson, we're interested in the probability of a discrete range of the count of occurrences. With the exponential, we want the probability of the interval in between occurrences. A Poisson distributed random variable might help us answer, what is the probability that 1 or more light bulbs burn out in the next 5 years? Whereas an exponentially distributed random variable might help us answer, what is the probability that a light bulb won't burn out in 2.5 years? The exponential PDF is f of y equals lambda times e to the minus lambda times y, where lambda is the same rate of occurrence from the Poisson distribution. Unlike the normal distribution, which had 2 parameters, mu and sigma, the exponential distribution only has 1 parameter, lambda, the rate of occurrence. The exponential distribution is a special case of the gamma distribution, and some textbooks refer to the rate of occurrence as 1 divided by beta, where beta is the mean length of the interval between occurrences. Therefore, 1 divided by beta would give the number of occurrences per interval. Some might find that thinking about the exponential distribution parameter as the average interval between occurrences is helpful, but I prefer to use rate lambda to show the similarities between the exponential distribution and its discrete cousin, the Poisson distribution. Unlike the normal distribution, the exponential distribution is truncated at 0. That is, the realizations of an exponentially distributed random variable can't be negative. The shape of the exponential distribution is called negative exponential or exponential decay in other fields. F of y intersects the y-axis at the value of lambda, then decreases from there as y increases. The smaller the lambda, the flatter the distribution. This should make some intuitive sense. If the rate of occurrence is smaller, occurrences happen less frequently, thereby leaving more probability for them to happen later on. Recall that the cumulative distribution, capital F of y, gives us the cumulative probability from the lower bound of the distribution, which in this case is 0, up to the value y. We calculate the probability by integrating f of y and evaluating between 0 and y. So what would the CDF be? As it turns out, capital F of y is 1 minus e to the minus lambda times y. Let's look at the expected value. Recall that the expected value of a continuous random variable is the integral of y times f of y, evaluated on the bounds of the distribution. For exponentially distributed random variable y, this is the integral of y times lambda e to the minus lambda times y, evaluated between 0 and infinity, as the exponential distribution extends infinitely in the positive direction. If you work that out, you'll find that the expected value is 1 divided by lambda. That's not surprising. If lambda is the average number of occurrences per interval, 1 divided by lambda would give us the average interval per occurrence, which would be the mean of the exponentially distributed random variable. This is helpful because if we know what the expected value is, say from sample data, where we find the average of some data sampled from what we believe is an exponential distribution, then we know what lambda is. Recall that the variance is the expected value of y squared minus the expected value of y quantity squared. If we work this out for the exponential distribution, we get that the variance of exponentially distributed random variable y is 1 divided by lambda squared. One of the famous properties of the exponential distribution is the fact that it's memoryless. That is, if we want to know the probability that the interval is longer than y plus b, given that we've already witnessed that the interval is greater than b, that's just the probability that the random variable is greater than y. It doesn't matter that we've witnessed the process or system for b time periods without witnessing the occurrence that we're looking for. The time to the next occurrence is memoryless. Such a property is useful for calculations, but it may not necessarily represent reality in many applications. So that's an introduction to the exponential probability distribution. We'll learn more as we do a few examples.